The Big Bang and the formation of the visible universe. In this video, we are discussing the Big Bang and its after events. Rather than the other models of the Big Bang, here I am taking space-time as an important factor. We are discussing the impacts that created in the space-time after the Big Bang. The influence of space-time to encourage the Big Bang is also an important factor here. At the very Big Bang moment, there was three important changes happening in the singularity and the space-time. These changes encourages the inflation era. The things that are happened in the Planck era are also discussed as the interaction between space-time and the singularity. As I feel the Big Bang as a breakdown of the singularity and the space-time, then it can never be an explosion. Also here we are discussing why the Big Bang happened at that particular time. This video is part of a series of videos describing the entire universe. I am starting from the early stages of the universe before the Big Bang. I am discussing the various situations for the formation of the Big Bang singularity. Then the cause of Big Bang at that particular time is also explaining here. In this video series, I discuss the subsequent Big Bang, the expansion, the structure, and the end of the universe. I illustrate all this with the help of a new concept that I have developed from my studies. So now we will discuss the Big Bang moment. Let us try to understand that. Had the particles inside the singularity are in equilibrium and how they went through a Big Bang and so on. In the Big Bang singularity, the energy and the space-time were separated from each other and tried to create an equilibrium system. So we can consider these two things as a closed system. Now you may ask that how the Big Bang happened in a universe that is so balanced in each other. Or you can ask that why did the Big Bang happen at that particular time? We know that the Big Bang singularity had the energy to encompass the entire universe what we see today. If more than a certain amount of energy is concentrated in one place, it is possible to be born a star over there. But we are not talking about its causes here. Then even though the energy contained in the whole universe that was concentrated in one place, why did the Big Bang not happen at earlier? Or why didn't the Big Bang happen a little bit later so that it can store some more energy into the singularity? One of the main causes for the Big Bang is the gravitational force, that is the fellow traveler of energy. Mainly there must be an unbalanced situation in the primordial universe. That's why the primordial universe, the amount of space or energy must have been greater than in one of these two. If the amount of space-time or energy is a little more or less, it will create an imbalance over there. This is the only reason for the subsequent Big Bang at that particular time. I can find the answers to many questions here that bothered me. In our visible universe, a star can be born if more than limited energy is concentrated in one place. Then why did the singularity so full of energy? The energy which can create the billions of stars and everything else that we see in the cosmos today not undergoes the Big Bang before. The primordial particles were so full of energy and there was no space left inside. We can understand how much it was balanced. Similarly, we can imagine a space-time can also say that it is perfectly balanced. The combination of these two created an imbalance in the primordial universe. As I said before, the ratio between the proportion of these two are unbalanced. When the primordial universe attempted to overcome this imbalance and with the help of gravity, the singularity began to form. As the singularity begins to form, the two particles merge together and becomes a single particle. What are the imbalances that causes the Big Bang in the singularity that is forming in a state of equilibrium? In any case, there was no space inside the singularity. The singularity was formed by expelling the space. As the singularity absorbs more energy, so does its gravity also increases. Maybe this has caused it to the tendency to shrink more. This may be increased its pressure too. And paradoxically, there was another activity. The increasing energy was also proportionally curving the space-time around the singularity. Even though it was expelled out of the singularity, the space remained as part of its space-time. For nothing can exist without space-time. We can already see many reasons which can break the equilibrium of the singularity. First, the pressure inside it, then the curvature it creates in the space-time where it exists. By increasing curvature in the singularity can also compress the space-time. In addition to this, as the amount of energy within the singularity increases, the imbalance between the space-time and energy also increases. A normal black hole singularity may not bend the space-time in such a terrible state. But when we talk about the Big Bang singularity, we have to think about this because it had the energy to create the entire universe. It would bend the space-time in a way horrible than we thought. The reaction of the space-time against it is perhaps one of the underlying cause of the Big Bang. Maybe the gravitationally curved spacetime also needs the Big Bang to happen. As far as I understand, spacetime is very flexible. Energy can use the spacetime as it pleases. When energy expels all the space inside it and enters a singularity, the spacetime around it is more likely to shrink. As the concentration of energy in a certain area increases, the characteristics of the spacetime over there also undergo some changes. So the spacetime around the Big Bang singularity must have been very much compressed. It was with such a force that the energy within the singularity was pulled the spacetime into it. The flexibility of the spacetime also changes according to the pressure exerted by the energy on the spacetime. And the movement and speed of the objects moving through it will change according to the flexibility of the spacetime. We have proved experimentally that light bends under the influence of the gravity. Space-time within the event horizon of a singularity must be very compressed. That is why even light cannot escape from there. This image is what I drew from my imagination in a way that everyone could understand. The horribly curved spacetime. The round spherical part of the figure indicates the Big Bang singularity. The grey colored top side shows its even horizon, and the black curved lines represents the terribly curved spacetime. In a picture representing a singularity, we usually see a cone-shaped curved spacetime. Things are a little more complicated here. The curved spacetime merged together for some distance. After that, its curvature slowly appears. We feel like a surface in a straight line was brought down, folded, and it is trying to bend it together with each other. This is just a two-dimensional picture. In fact, a spherical singularity creates a curvature of space-time from all its sides. When you try to fold the space-time with such a force, naturally there creates an imbalance. There was such a powerful activity because that much energy was involved in that region. Anyway, by taking advantages of all these imbalances, the Big Bang happens. There is another point to consider. Does the singularity occur only one place in the universe? We can never be clear about this. We have not been able to understand the boundaries of our universe or its vastness. Let us just say that the universe is infinite. Therefore, similar singularities may have been formed in many parts of the universe. Sometimes they do not store enough energy to happen a Big Bang. Sometimes there was a Big Bang happen in a singularity elsewhere. It may have expanding and become closer to our universe. It may also share a space-time with our universe. Let us go ahead hoping that everything is good for us. We cannot tell how much energy the whole universe had. But in future, we may calculate how much energy have in our universe where we live. Because our universe was formed from a singularity that stored at exactly the finite amount of energy. We have talked about the circumstances surrounding the Big Bang up to now. Now let us see what happens after the Big Bang. We have a clear understanding of that now. However, in my view, I would like to explain it more simply. I have been able to explain scientifically what happened after the Big Bang. With the Big Bang, our universe has to change its state into an expanding universe from its previous state of a singularity. When switching from one situation to another, the first thing it's tried to do is to maintain its stability. But we have three different scenarios here at the same time. First, the singularity continues to store energy until the moment of the Big Bang. Second, the state of singularity that has existed since that moment has ceased. Finally, the universe is starting to expand. At the same time the singularity breakdowns and the Big Bang occurs, the energy flows into the space-time. At the same time, the space-time also undergoes through three different situations in a similar way. As each particle is added to the singularity, the space-time is also increases proportionally, and there is a loss of stability of space-time. Finally, when the Big Bang happens, the space-time collapses down and penetrates into the singularity. Moreover, the imbalance between the ratio of the space-time and the energy will reach its maximum. One particle dissolves into the singularity and many other particles are approaching the singularity. This was the scenery at the time of the Big Bang. The Big Bang was never an explosion. The Big Bang is a breakdown of two equilibrium states of interaction. Space-time and singularity are undergoing some changes at the same time. Both are simultaneous processes. This is an ongoing phenomenon. As the universe expands into the space-time, changes will also occur in the space-time, which is curved by its gravitational field. Here we can try to view the universe as two basic forms, energy and the space-time. Energy with the help of its own gravity causes changes in space-time and expands into it. The universe is a mix of functional reactions between energy and space-time. Space-time may also be trying to survive the changes created by the energy in it. All these situations are well described in my book, The Key to the Secrets of the Universe. You can see the evolution of the universe from the primordial stage until the destiny of the expansion of the universe in my book. There you can see a lot of new ideas on the expansion and the acceleration of the universe and about the gravitational interaction. I am explaining there how the expansion of the universe is undergoing another Big Bang. You can find the link to the book in the description box. Anyhow, things happen from 0 to 10 raised to minus 43 seconds after the Big Bang are still unknown to us. But I will try to explain the situations of that period. 10 raised to minus 43 seconds is a shorter time that we cannot imagine. Think that if we write 43 zeros before 1, and how small is this? In physics, such a short period of time we call it as Planck time. Hence, the period from the Big Bang to this time is called as the Planck age. So we can assume that the Big Bang happens in the 0th second. The new time which begins with the Big Bang will be added to the collapsed space. A new space-time will be created there. Space-time must have been created along with the Big Bang. Otherwise, there will be a time difference between space-time and the Big Bang. For example, suppose the space-time is added to the space after the Planck age. Then there will be a big difference between the timeline of the Big Bang and the timeline of the space-time. Right away with the Big Bang, the situation already existed there is changing. The energy stored as a singularity is released. A massive disorder in the curved space-time by the singularity will be happen. The energy from the singularity will start to spread in the space-time. In this case, both systems will attempt to regain the lost equilibrium. The singularity of the Big Bang and the space-time destroyed by the Big Bang will prepare for each other. Singularity is said to exert its energy to spread into the space-time, and the space-time will prepare to accommodate it in. This kind of the preparation must have been done during the Planck age. For that, the Big Bang singularity will be releasing a massive temperature. The space-time will absorb it. This will cause the temperature of the universe to decrease. As we know it today, the four fundamental forces that we know in the universe are appeared together during this period. The four fundamental interactions, namely strong interaction, weak interaction, gravitational interaction, and electromagnetic interactions, were separated after the Planck age. At the end of the Planck age, the gravitational interaction dissociated from the electronuclear interactions that has held it together. Gravity stays part of the energy and the other fundamental interactions become free. The inflation era then begins as the result of these preparations. We can realize that inflation has an important role in the expansion of the universe. After the Big Bang, we can see that there is an acceleration occurring in the expansion of the universe. The expansion of the universe in this stage was at an accelerating rate that much faster than the speed of light. The inflationary epoch started 10 raised to minus 36 seconds after the Big Bang. This may have lasted up to 10 raised to minus 32 seconds. During this period, the space-time which joined together in the Planck era began to penetrate into the distracted singularity with a massive velocity. At the same time, the energy released by the Big Bang began to penetrate rapidly into the shattered space-time. Both of these things happens at the same time. We can describe this as an interaction between energy and the space-time. Here we see the space-time and energy are acting as motivating forces to each other. The space-time inspires energy to penetrate into it. Similarly, energy invites space-time to penetrate into it. This is the reason for the tremendous acceleration of the cosmic expansion during the inflation period. In my opinion, physics is a true understanding of the characteristics of the universe. The nature around us provides all the answers to its phenomenon if we look at it carefully. Inflation made me think a lot about the Big Bang, the force that created by the Big Bang, and the after effects of the Big Bang. It causes me to think deeply about what we do in our daily lives. I understand that we can keep track of inflation in every activity that we apply a force. In my logic, inflation is the effect which is created by an external force when it is affecting an object or another force. We can view it in all actions. For example, we can observe a billiards board. Here I am taking two balls as the example. When a ball hits to another ball, the kinetic energy shifts from it to the another. So the second ball is gaining momentum in it. The influence of the external force from the first ball will fulfill all the parts of the second ball uniformly and abruptly. This will be a driving force for it to move. Because of this, it gains a sudden acceleration and we can call it as inflation. And the speed of this uniform filling of the force to the object will depend upon the strength of the force. If the applied force is weak, it will affect the body slowly. The force that was created there during the Big Bang is beyond anything that we can imagine. We can see that this will be a lot more influential in its later journey. Now suppose we are applying a force on an object traveling at a straight line. The trajectory of the object also changes depending on the force that we are applying. Depending on the nature of the force we are applying, it may increase or decrease the velocity of the object. We have learned these all things in schools, but relating all these things with the phenomena which occurred in the time of the Big Bang is more challenging. But we have to do such a correlation because the universe has only one law. Whatever things happen anywhere in the universe must have to explain in a similar way. Even if it is the Big Bang that triggered the cosmic evolution or any small action we do, it will all happen under the same law. We are experiencing these things in a different manner. There were many developments during this period of the Big Bang. We can never experience all that in the small activities we do. For example, during the Big Bang, massive amount of energy are emitted and the fundamental forces were freed. None of this will appear in our actions. This is because of the strong force created there and then by the nature of the singularity. But there may be something similar happen in our actions. There is much more to be learned about it. Let us return to the billiards ball. When the ball hits on the other ball, we can observe some kind of vibration on the ball and it will make a sound too. We can say that this is a reflection of the force we applied. At this point, the ball will make an effort to stabilize its state of being. At the same time, the applied force to it is eventually distributed to all its parts. We can compare this period to the Planck era. Almost of all these two things have happened in the Big Bang Singularity and in the curved spacetime where it exists. Once the force is evenly distributed, the next phase has begun. Thus, they were preparing to accommodate the changes. On the other hand, the singularity is preparing to spread to the spacetime for the state of unity. Same time, the spacetime curved by a strong gravitational field is preparing to absorb the sudden changes. The phenomenon of the Big Bang breaks the states of the singularity, so does the state of the spacetime also. Once an equal amount of force is distributed, the other fundamental forces within the singularity can be freed. At the same time, to avoid the disturbance within it, the damaged spacetime will apply a strong force to the shattered singularity. This period in the Big Bang was marked as the Grand Unification Era. The next phase of the inflation era has begun as the continuation of these events. Here, energy can enter to the spacetime very quickly. The advantage of this phase is the spacetime is applying a force over the singularity. Likewise, the spacetime appears to absorb the energy into it. This causes a sudden acceleration of the expansion of the universe. If we take a closer look at these periods, we can describe the universe in more detail. Even the separation of the basic forces each other in the different states. When we talk about the Big Bang, we are always talking about the phenomena that occurred in the singularity only. In my opinion also, space-time must have the same importance as the singularity, because singularity cannot exist without the space-time. Singularity is a phenomenon with full of pure energy. Energy always needs some space to survive. That's why Albert Einstein included space-time as the fourth dimension. The three dimensions of energy with the fourth dimensions of the space and time together. Then we have to understand the changes that have been created in the space-time by the Big Bang. I would like to say that these two processes happening together. Many have overcome forward with the idea that there was no space or time before the Big Bang. I can never accept it. I believe that the universe exists only if the space and energy coexist. Let us now take a short look at the events from the Big Bang to the expansion of the universe we see today. Each period of the time needs to be well explained. I would like to go ahead and explain these periods in a very lucrative way. For the sake of the completeness of this video, it may be presented again very simply. After then, we can discuss the structure of the universe. So the Big Bang happens in the 0th second. Then the Planck era up to 10 raised to minus 43 seconds. We have already discussed the Planck age in detail. By the end of the Planck age, the gravity was free from another fundamental forces. This starts the beginning of the Grand Unification era. By this time, the universe is starting to emit a massive amount of temperature. In addition, all the three fundamental forces other than gravity appear together to be an electronuclear force. It lasted about 10 raised to minus 36 seconds. By the end of this period, the strong nuclear force has been liberated from other forces. This allows the formation of nuclei of small atoms. At the same time, the nature of the space-time must have been more flexible. The space-time that was part of the singularity was very much compressed. Flexible space-time is adapted to the new changes that have taken place in the universe. This allows the newly formed particles to move freely through the space-time. This allows the particles to easily distort their own space-time. Then came the beginning of the inflation era. It lasted about 10 raised to minus 32 seconds. As space-time became more flexible, the high temperatures created by the Big Bang can be distributed very quickly in the space-time. This will help to reduce the temperature of the universe. Henceforth, the space-time will play a major role in determining the structure of the universe according to the energy distribution of each period. Since then, the universe has moved on to an electroweak era. In this period, the weak nuclear force and the electromagnetic force are seen as a single force. This period was conducive to the production of heavy but rapidly decaying bosons. It lasted about 10 raised to minus 12 seconds. Then the quark era is about 10 raised to minus 12 seconds to 10 raised to minus 6 seconds after the Big Bang. It is at this stage that the four fundamental forces that we see today begin to be distinguished from one another. That is, the rest electromagnetic force and the weak nuclear force were separated from each other. It may be assumed that quarks and leptons were formed at this period. Then the period of up to 1 second is called the hadron age. During this period, the temperature of the universe was greatly reduced and allowing the quarks and leptons to bind together to be converted into hadrons. At the same time, all the opposites of these particles, like antiparticles, is being created. Later in this process, they are undergoing through annihilation. During all these periods, the energy was being circulated in many forms into the space-time. The phenomenon known as neutrino decoupling is thought to have begun a second after the Big Bang. Today, the most abundant neutrinos after the photons in the visible universe begin to travel freely during this time. Detecting these neutrinos having very little energy is very difficult with our present technology. It is thought that billions of neutrinos move around us every second. During this time, the temperature of the universe was still high enough to create also electron-positron pairs together with neutrinos. After about 10 seconds, the temperature changes of the universe led the electron-positron pairs to the point of annihilation. The period from 1 second to 10 seconds is also called the lepton age because there are still a small number of electrons left after this. The energy generated by the annihilation of the electron-positron pairs caused the creation of photons. This period is therefore called as the photon age. Within the first few minutes of this period, a process called nucleosynthesis takes place in the universe. From approximately 2 to 20 minutes, the temperature of the universe helps for the formation of the nuclei. So this time duration we call the nucleosynthesis period. It was during this period that the initial forms of the atomic nuclei that we see today were formed. The first nuclei were formed by combining photons and neutrons that were be able to take advantage of the favorable conditions. At this stage, nuclei are formed similar to smaller elements such as hydrogen and helium. As the universe expanded, its temperature and density begins to decrease. By this process, it took nearly 100,000 years to formulate the first molecule. We can call this period as the invisible universe. During all this time, the universe did not allow to pass the light. Therefore, the universe was in a dark stage. After 370,000 years, the universe has become transparent and allows light to pass in it. The changes occurring in the universe during this period are in favor of this. The temperature of the universe for about this period follows the formation of atoms. They create a situation to allow the freely rotating electrons to combine with the hydrogen and helium nuclei that already formed to create a neutral atoms. This combination of the electrons and the nucleus will release the excess energy in the form of photons. With the formation of atoms, the space-time is more flexible and allowing the photons to travel freely. Thus, we see the universe is gradually becoming transparent. So much so that is going on. Now we can say the basic fuels for the formation of the stars has been created in the universe. However, we cannot say that the stars immediately formed. There is a need of the favorable situation for the star to be born. Studies suggest that about 380 to 400 million years were taken for the first galaxies to be born. This is how we explain the evolution of the universe in general. We will not talk about the space-time where the energy or matter exists. The cosmic evolutionary structure in my mind involves the reaction of space-time according to the changes in matter. So in next video we will discuss the structure and the formation of the universe. Thank you for watching.